Okay, page 19. So number one, we're asked to find the derivative of some integral notation. This looks messy, but we know that this is basically the setup for second theorem. So second theorem says that we can take the derivative of that integral, and that really can just kind of line up with the formula that we're going to apply. Again, this looks like chain rule, but it's not really chain rule. It's just really a shortcut to the end of the problem, rather than having to go through two separate um, processes that end up canceling each other out. So if we know that they're going to cancel each other out, we can save some time by just doing what is needed to get to the end. So the upper bound is going to get inserted into the expression, and then the upper bound is going to get its own derivative taken care of. So here we see e to the 4x squared being the expression. I'm just going to plug that, or e to the 4 t squared. I'm just going to insert that z into that t. I can only do this process if I see these two operations undoing each other, right? We can't do that if I just see the integral there. It's got to be these two opposite operations on top of one another. Okay, so e to the 4z squared, sorry, that's a z, e to the 4z squared times the upper bound's derivative. Upper bound is z, so z's derivative is 1. That constant 0 will just go away. And there's no plus c. There would be plus c if we just took the antiderivative, but the derivative is going to wind up undoing and canceling any c's left over, because any constants will just go to 0. Okay, let's look at number 2. If the depth integral from 0 to 2 of 2x cubed minus kx squared plus 2k is equal to 12, then k must be. Let's just do this problem and pretend like we don't see the 12. And let's just do it the way we would normally do it. Okay, so I got to go through the appropriate antiderivative rule. All right, and then I got to plug in the 2 and 0, and let's just see what happens, right? Let's see whatever we get in return, we can then deal with that 12. But and then we see something a little strange here, and that's that k. Right? What does that k mean? Just treat k as an unknown constant. Okay, so it's not a variable, it's a constant. So treat k as an unknown constant. So however way you treat constants, that's the way you're going to treat k. All right, the nice thing about this problem is every term is set up and ready for what rule? Just power rule, right? Just easy power rule, no messy u substitution, no expansion necessary, no cleanup necessary. Jump directly into our power rule. K is just some number hanging out in front, so k is just going to stay. We get x cubed over 3. And what does 2k become? 2kx, that's right. Yeah, not 2k squared over 2. That's just some number. That number is going to rise up to a degree 1. Okay? No plus c, because we see the bounds involved. So we know we can work in those bounds. Okay, so 2 goes in for x. minus, we're going to evaluate all the lower bounds as well. So let's clean this up here. We get 2 to the 4th is 16. 16 times 2 is 32. 32 divided by 4 is 8. Okay, so that's our answer. That's as far as we can get by itself. But then we realize, oh, it's equal to 12. So now we have an equation that we can solve for k. Okay, combine some like terms here. 12 minus 8 is 4. And then the remaining terms, I want to try to do common denominator so I can get all this cleaned up. So my common denominator is 3 in the denominator. Sorry, it's a 1. My common denominator is 3. So numerator stays. Second numerator I need to multiply by 3. Negative 8k over 3 plus 12 over 3k. Can combine those like terms now that they are common denominators. I get 4k over 3 is equal to 4. I'm going to force a 1 below. Makes it easier for me to see that I can just cross multiply and solve for k. Okay, number 3. Number 3 looks like, well, we know that if there is only one term in the denominator, we can split up into individual fractions. There's more than one term. We know it's too complicated for power rule or moving up to the top. We got to go through U substitution. Right? Anything that feels messier than power rule, we got to go through U substitution. Okay, so what's our U value? Yeah, that's a denominator, right? The denominator, we usually want our U value to be a generous portion of the problem because we want the problem to change significantly to a simpler problem, right? And if we let our U value just be a portion, a small portion, it's not enough to get it cleaned up. We want it to be a significant chunk of your problem. Okay, and also that denominator degree is helpful as well. You know that degree 2 is going to do its work to help you get to a degree 1 that will cancel that numerator out. The x's cancel out. There's a leftover 2, but it's in the denominator. Push that 2 out as 1/2. So this is really the benefit of U substitution is that you've rewritten the problem in a form that feels a lot more familiar. We know a rule that we can apply here, natural log. And then bring your original variable back, where U is x squared minus 4. Okay, questions? Page 19. Okay. All right, 20th base of a solid is a region in the first quadrant bounded by the x-axis, y-axis, and the curve x squared plus 2y equals 4. Again, we're dealing with cross sections of squares. Find the volume of the solid. It's hard to visualize what this graph may look like, so we want to solve for y so we can have a better idea as to what it could be. If I can divide both sides by 2. So if I rearrange this, I can see that it's really just -1/2 x squared plus 2. So we know that's a parabola with a y-intercept of 2, and it's going to open down. That -1/2 just makes it wider, but you know it's just a downward parabola with a vertical with a y-intercept of 2. Okay, so this is normally our parabola, but we're talking about the first quadrant. So we want the parabola, the y-axis, and the x-axis. So it's going to be this little quarter circle looking region here. Okay, perpendicular to the x-axis. Which direction is that? Up and down, right? So x-axis is this way. Perpendicular is 90 degrees to that. So no rotation, no axis of revolution. Whatever direction we discover, that's the direction of our base. So our base length is vertical. Okay. As soon as you see that base length, you know it's top minus bottom. Top minus bottom is easier because your equation is ready for you to use. In this case, we had to do actually I do a little bit of rearranging, but this feels familiar here. We know the curve is the parabola. We know the bottom is the y equals 0. Okay, so the top is the parabola, the bottom is the 0. We built the base. The area is the base squared, and then the volume, we just give it that third dimension, put the integral around it, and it gives it that third dimension. Our bounds is from our furthest left to furthest right, so it's from 0 to whatever this value is. I can set the equation equal to 0. Or I can use my calculator. And I multiply both sides by -1/2. I get 1/2. I got x squared equals 4, x equals plus or minus 2. So I know -2 is not going to make sense because that's over here in the second quadrant. We're only going to go from 0 to 2 because we're only dealing with the first quadrant. I think the rest we can enter into our calculator. But if we didn't have our calculator, you would expand it. You still do this, but it's just a little longer. You got to expand all this out, fill all this out, and then plug in the upper and lower bound. Now, if you get to this point, and because I'm giving you a calculator, you can just plug this into your calculator. Okay, questions so far? The function f is continuous on the closed interval, and the values of the function are shown. If the values in the table are used to calculate a trapezoidal sum, the approximate values of the interval from 1 to 5 are, so trapezoid area not base times height. It's a little bit more involved than that. It's 1/2 width, height 1 plus height 2. Now, every trapezoid only gets 2 heights. So if I have a span of multiple heights, I'm still going to just pick the ones at the end. Okay, so I see some students want to add up all the heights they see in front of you, but every trapezoid only needs 2 heights. So in this case, though, we have more than one trapezoid. It says use the values in the table. So that means every subinterval, you're going to have to create one trapezoid. Okay, so here, normally it's not as easy as this where your width are all the same distance away. But in this case, it is. All the width is going to be 1. Okay, so let's build our trapezoid here. Again, we know this is just an approximation of the actual antiderivative because this doesn't adapt to all the changing regions. However, a trapezoid is the most accurate of all the approximations. So trapezoid is typically the best approximation, and then it's your middle or your midpoint Riemann sum, and then your left and your right. Left and right we don't really know which one is more accurate. Depends on the situation. Okay, so 1/2 width. So my first interval, my width is 1. My heights are 4 and 3. Okay, so all my widths are 1. My second trapezoid is 3 and 7. Seven plus 1. Okay, so just add all that up. Ends up giving us 14.5. I like to treat this as well, you know that f of x is the antiderivative of f. What that means is, so it says that f of x is the antiderivative of lowercase f. So what that means is that this f, lowercase f, is really uppercase f prime. Okay, so whatever we're staring at here is really uppercase f prime. So I like to think of it as, oh, okay, if I'm trying to find, now I could go through this process and take the antiderivative, find the c value using this, and then use this plugin again. But I like to think of it as anytime I can think of it as a particle motion problem or position displacement problem. I can think of it as, oh, this is my final position, this is my initial position, and then the integral of this is my displacement. Now you can enter this into your calculator, but I just want us to practice a bit with U substitution because this can be done using U substitution. Okay, so square root of 9 is 3. 3 times 3 cubed is 27. So 26 over 6 is the result of this whole mess. So if this showed up on the non-calculator portion of your AP exam, this is what you have to do. Okay. Okay, number 7. Uppercase f and lowercase f are continuous functions such that f prime equals f of x for all. Definite integral from 2 to 5 of f of 3 of x equals. So we don't have enough information for us to find power rule and all that, but we can go through substitution, and we do know that lowercase f through its antiderivative will turn into uppercase f, and all we know is, we just have to match it up with the correct antiderivative in terms of uppercase f. So let's go through substitution first, because we know that 3x is going to have some leftover associated with it. I'm not going to deal with the balance just yet. I'll deal with that when I clean everything up. So I can pull the 1/3 out in front. F of u du. Okay, so we're ready. This is nice and clean. Lowercase f is going to rise up to what? What's the integral of lowercase f? Capital uppercase f. So we know it's going to turn to 1/3 uppercase f of u. We know we got to work in the balance, but can I just plug in the 2 and 5? Yeah, so right. So either one of two things, right? You either get the 2 and 5 in terms of x, and also turn this back in terms of x, or if you want to leave this in terms of u, you got to convert the 2 and 5 to be in terms of u. But right now the 2 and 5 exist as x, which is fine. I think most students prefer to just bring the original variable back, but just make sure that you're matching variable with the correct variable with variable. So x here, x is here. So now we can plug in the upper and lower bound. But you see how they are prepared for students to make that potential mistake. Okay, what they did was they factored the 1/3 out, but it's the same thing. Okay, number 8, average value. That's a hint. Average value theorem. Okay, so set up your average value theorem. Replace the a and b with 0 and 4. Replace the f of x with e to the 3x. Now we're just solving this relatively manageable definite integral, right? But make sure you take your time. The 1/4 is going to stay out in front. We do have to go through a little bit of what? Yeah, use substitution, right? That's 3x. We know something's going to come out of it, so we do want to take our time with it. We let our u value be 3x. Should clean up nicely. U equals 3x. Du dx is 3. Solve for dx. Dx equals du over 3. You make your substitutions with the 3x and the dx. 3x is u, dx is du over 3, and that helps remind us that we do have to keep track of some leftover coefficients. So push that 1/3 out along with the 1/4, make it 1/12. Now we just have a relatively easy problem to solve. We know integral of e to the u is just what? Well, that's chain rule. E to the u is just e to the u plus c, right? But we can do away with the plus c because we know the bounds are going to involve itself. So we know e to the u is just e to the u. I'm going to bring back my original variable. And that way I can just handle my, use my original bounds. Okay, upper bound first, minus, then lower bound. Careful with zeros. I think the tendency is if we're not careful, we always associate 0 with just wiping everything out. But in this case, the 0 is an exponent, so e to the 0 is still a 1. So there's going to be some leftover there. E to the 0 is 1. There's still that 1/12 here, so it's really 1/2 e to the 12th minus 1/12. Which I think the answer choice merged it back as a one fraction with using common denominator there. So if you look, they're prepared and ready for with answer choice C in case you made a mistake and associated the 0 with a 0, right? So yeah, just be careful. Okay, solving differential equations. We know that we can cross multiply first to get our variables all lined up in the numerator, and then we can decide, okay, what do I need to do to divide and get that y by itself. After I cross multiply, the nice thing is I'm already sitting at my variable nicely separated. E to the y dy is all y's. X's are together. Okay, I'm ready to take my antiderivative. Now that I have full separation of variables. The nice thing here is, I mean, I can go through u substitution, but it's just the same variable here. So if you understand that the y is just u, then you know e to the y is just e to the y, right? We can't go through u substitution if you feel more comfortable, but if it's only one variable, I would say you can make that adjustment without having to worry about it. Sorry. Let's say the plus c for the other side. Sine of x, what's the integral of sine of x? Negative cosine of x, yeah. So that's a relatively easy process here. We found the antiderivative. I think the messier part is trying to do the algebra portion, trying to get that y by itself. There's two things left to do. We got to solve for c, and then we have to worry about solving for y. Okay, maybe I can just solve for c now. Again, I don't really have a rhyme or reason as to when I solve for, do I solve for c first or do I solve for y first? I just kind of look at the problem and decide, okay, if it feels like an easy point for me to solve for c, I'm going to go ahead and do that. But if it looks like c is going to be tough for me to do without doing a whole bunch of algebraic steps, then I wait till the end. So I'm just kind of, but it's not right or wrong. If you solve for c at the beginning or solve for the end, you really can just ultimately just know you got to solve it at some point. Okay, so pi over 4 in for x, 0 in for y. Make sure you also review your unit circle values. That's important, not only for the test, but also with AP exam. You really want to be able to, especially on the non-calculator portion, we need to be able to go far enough. We never can leave our answer with the trig unresolved. So make sure you review your unit circle values. Okay, so 1, we know cosine of pi over 4 is √2/2. Negative is going to stay just because it's part of the problem. I can add that √2/2 over to the other side. Okay, so I'm going to bring back my original, or I'm going to replace the C with what I found here. And then see if I can get that Y by itself. Okay, one thing left to do is to solve for the Y. To solve for the Y is stuck in the exponent location. What can I do to both sides to get that Y to come down? Take the natural log, right? Natural log allows exponents to come down. Okay, push that Y in front. What happens with natural log of E? Goes away. That's just equal to 1. The order of the terms are not the same as the answer choice, but that should be easy for us to adjust. Answer choice B. Okay, everybody good? Page 21. Okay, last page, 22. All right, definite integral, root x. So this one, this is meant to be done by hand. Obviously, if you saw this, you can enter into your calculator and work backwards to show the steps. But in this case, if I want to work this out by hand, I see a bunch of parentheses here, but do I need to go through use substitution? Remember, there's no product, quotient, or chain rule for antiderivatives. But can I rely on a simple rule to go through this process? Yeah, if I expand everything out, it's doable, right? Because there's no like, if it was like square root of this whole expression, then I'm kind of stuck, right? But this is manageable. It's only that square root is only for that one term. I can clean it up, distribute through, and just rely on power rule at the end. So yeah, expand all the way out. Power rule should get us our answer. And that's also a good reminder that whenever you see an antiderivative problem, especially if it's non-calculator, we don't want the parentheses to throw us off, right? We always want to consider, okay, my first option is expansion. Can I just go through simple algebraic methods to get it cleaned up to the point where I can just rely on power rule? But as soon as you see numerator, denominator has more than one term, square roots, making an expression really complicated to work with, then your second option is use substitution, right? But we don't want to always assume that anything with parentheses is going to be use substitution, right? Because use substitution is not going to work for this problem. It's meant for us to expand. Okay, add exponents, 1/2 plus 2 is 1/2 plus 4/2, which is 5/2. 1/2 plus 1 is 3/2. Then every term is nicely set up for power rule. We add 1 to the exponent divided by that new exponent. No need to do a plus C. There are bounds involved, so we can use 0 and 1. Upper bound first. I'm just going to flip all my denominators up and multiply with the coefficients in front. So 3 times 2/5, 8 times 2/3. The zeros, it looks like in this case, 0 does wipe everything out. But we always want to make sure and convince ourselves that there's nothing hidden. There's nothing tricky going on, right? In this case, the zeros do go away. So 2/7 plus 6/5 minus 16/3. Yeah, it's a messy fraction, but you could use your calculator to find the appropriate choice. Okay, number 11, you see the word revolved. You know it's got to be either disk or washer method, volume problem. Okay, y equals 2, y equals square root of x. You got a radical function, you have y equals 2, and you have the y-axis. Revolved about the y-axis. So here's my axis of revolution. Disk or washer method. Disk, because the shaded region has a flat surface right up against that dotted line, right? There's no need for 2 radius, just 1 radius is enough. Okay, radius is going to extend horizontally. So that is also a bit of a red flag, right? We know we have to do some work to get the equations in the correct spot, because this y equals root x is meant for top minus bottom. It's not built for the right minus left radius. Okay, so I got to solve for x, square both sides. The curve is the x equals y squared. Okay, build our radius. Right minus left, the right endpoint of my radius is touching the y squared, the left endpoint is sitting at the 0. Our bounds are also in terms of y. What's the lowest y value that you see? What's the highest y values? There you go, 0 to 2. Now you can obviously use your calculator, but this is something that could show up on the non-calculator portion of your AP exam, and that's completely manageable within reason, because you can just clean this up easily, go through the power rule, and plug in the upper and lower bound. And so I don't want us to forget that process. Units cubed. Okay, 12, let R be the region. You got y equals x squared, x equals 4, and the x-axis. Which of the following? Again, we're rotating about the y-axis. You know it's going to be either disk or washer method. Y equals x squared is a parabola that goes through 0, 0. X equals 4 is a vertical line. So we know it's not going to involve the second quadrant here because it doesn't create, there's nothing that's going to enclose this region. It's only talking about this first quadrant. Because every boundary that they indicate has to be the boundary of our shaded region. Okay, rotating this shaded region about the y-axis. Okay. Disk or washer? Washer. So we see that there's not a flat surface lined up against this axis like the previous problem, right? There's a huge gap here. Even though it is touching at 0, 0, this gap is enough for us to indicate that we need to subtract out the whole from this volume. So we need two radius, big R and little r. Again, horizontal radius. I purposely picked horizontal radius so that we can practice with the right minus left, because that is the one that students find more challenging, right? Taking the time to rewrite the equation in the proper form. So this vertical line is x equals 4. You got the y-axis, which is x equals 0. You have the curve. The curve needs to be rewritten as well. It was y equals x squared. I do need to solve for x. I need to square both sides, square root both sides. Technically, it's plus or minus root y, but we're only talking about the first quadrant, so only positive root y. Okay, let's build our two radius, big R. The right endpoint of my big radius is sitting at the 4. The left endpoint of my big radius is sitting at the 0, so 4 minus 0. Okay. The right endpoint of my little radius is sitting at the root y. The left endpoint is sitting at the 0, so root y minus 0. Our bounds, we want to know, go from the lowest to the highest y value. Lowest is 0, but the highest y value is whatever that y value is when x is 4, right? We know when x is 4, so rather than having to create a messy equation, let's just plug 4 directly into the curve and find that y value, right? I can just do that. That's right. If I put 4 in x squared, I get y equals 16, so that point must be order pair 4, 16. So that's my upper bound. Now, this is technically also manageable by hand. You could clean this up, power rule, upper and lower bound. Okay, last one. Pizza heated to the temperature of 475 degrees is taken out of the oven, placed in a 105-degree room at 0 minutes. Temperature of the pizza is changing at a rate of this -236 e to the -0.7 T degrees Fahrenheit per minute. So you know that once that pizza is taken out of the oven, the temperature of that pizza is going to continually drop, right? And it says to near temperature, what's the temperature of the pizza at 9 minutes? So I know this is my quote unquote derivative. And I can think of it as, oh, this is really a final equals initial plus displacement. The temperature is at 475 degrees. Now that 105 degrees room temperature is built into this formula, so we don't have to worry about that. That's kind of there to distract us. So if I want to find the temperature of the pizza, I'm just going to create some variable here, P, representing the pizza temperature. We know the temperature of the pizza at 0 minutes, and then we got to figure out what change is happening in that 9-minute period. So this process will give us the change in temperature in that 9-minute period. So whatever 475 degree, whatever we know it's going to start at 475, and then however much temperature drops, we can add that to here, and then we can figure out what the actual temperature of the pizza is at 9 minutes in. Okay, this in the calculator will give us -365. So we know that this pizza is going to drop 365 degrees over the course of that 9-minute period. And then after 9 minutes, we can figure out what the temperature of that pizza is. 110 degrees. Okay. So no morning review tomorrow. If you want extra practice, I would say go ahead and chip away at packet number 6. You got a bunch of multiple choice problems there. You can just pick out the ones that are antiderivative or involving second semester topics and work through that. All right, let me know if you have any questions.
But it sort of said it doesn't give us like use like 3 problems.
Right.
Use every
With
single
everyone,
one.
yeah. If they just say, if they give you something vague, like
Mhm.
use the values in the table, that means every single one.
Okay.
Otherwise, they have to specify how many trapezoids or rectangles they want you to use.
And then for the one that was like this one, so when you plug f of u in, you change it to the big F prime of x, and then
Mhm.
once you take the integral of that, it's
uh-huh.
gonna become big
Big F,
big
yeah,
F. It won't go back to little f.
exactly, right. You can think of little f as big F prime, if that helps.
Okay.
Big F prime is gonna rise up to uppercase
Okay.
F, yeah.
Awesome. Thank
Mhm.
you.
You get a calculator, no formula sheets, but like the first test, yeah.
I was like, now it's not a good time, that's okay.
Um,